Hi, and welcome to Advanced Machine Learning. I'm Victor Banks, and right now we will get to know the follow the regularized leader algorithm, which is an alternative to the follow the leader algorithm, which is quite stable for online linear optimization problems, as we saw previously that the follow the leader algorithm might fail for these type of problems. And this will be done by, as the name suggests, introducing a regularization term, and we will get to know how to choose a suitable regularization for the online linear optimization problems. All right, so as I already said, the follow the regularized leader algorithm is essentially the follow the leader algorithm with an additional regularization term. So we have a regularization function, psi, which is mapping an action to some non-negative real-valued number. And this regularization function is encoding more or less some desired properties we want for the action. Quite similar to what we know from the batch learning scenario, where we have the regularized risk, where the regularization function, for instance, the L1 norm, is giving an incentive to have sparse models, that most of the parameters are 0. And you can do something similar here in the online learning world by introducing this regularization function into the choice mechanism of the follow the leader algorithm, and encode whatever you want, more or less, regarding the desired properties of the corresponding action. And once again, it might be the case, even if we have a regularization term involved, that there are more than one actions which are minimizing this expression. So the cumulative loss as before for the scene data plus regularization, it might be that there are more than just one. And then we just pick one of them due to some tie-breaking mechanism. And well, this is the follow the regularized leader algorithm simply. As you see, follow the leader is here still somehow present, but we have now additionally this regularization term, so that we have this additional notion of a regularized inside the name. And well, what's the interpretation of this action mechanism? So we still kind of follow the leader in terms of the leader with the smallest cumulative loss so far, but the leader also has to have some desired properties which are encoded in the regularization function. So we also add to the cumulative loss this term which is representing desired properties we want to enforce on the corresponding action. And we see we have here a lot of degrees of freedom for choosing this regularization term. And of course, if we do no regularization at all, so we simply set this regularization function to be 0 for every action, we recover the follow the leader algorithm. This is a quite nice property, because when we deal with an online quadratic optimization problem, we can simply get back to the follow the leader algorithm, for which we know that the follow the leader algorithm works quite stable, works quite well, has theoretical guarantees in terms of its cumulative regret, and also enjoys a cheap update formula, because it's then essentially the empirical average over the seen environmental data points, yeah, which we can update quite quickly, as we saw. But of course, yeah, we can also regularize, especially when we deal with problems, yeah, like the online linear optimization problem, where the follow the leader algorithm is not always stable, yeah, and we can make it more stable, more robust by choosing an appropriate regularization function. And before we do this, let's discuss this regularization term with respect to the batch learning scenario, where we also have regularization terms involved when we do empirical risk minimization. So what we do in the batch learning scenario, where we have again the strictly separated training and test phases. In the training phase, what we do is we look at the risk, empirical risk, which might be augmented in the sense that we add here a regularization function with some regularization parameter, which is also somehow collecting or describing desired properties on the parameter theta for the model. Yeah? Again, the L1 norm example, where we have the lasso regularization. This is enforcing that, for instance, a linear model will be rather sparse, that most of the thetas will be 0. And the difference here is that in the batch learning scenario, this is kind of our objective function. So this is the objective function which we want to minimize during training, more or less. So with the regularization, we can also get rid of overparameterization and overgeneralization. But in the online learning world, there we don't have this here as the objective function, because the objective function in the online learning world is still the regret, the cumulative regret. And in the cumulative regret, usually you don't see this regularization function. You only see the cumulative loss, compare it with the cumulative loss of the best action in hindsight, but you don't add some regularization to that. So this regularization for the follow the regularized leader algorithm is not part of the objective function, but it's rather used to guide the action or decision rule at each time step, so that we make sure that the actions are having nice properties, are not unstable or something like that. All right, then for this follow the regularized leader algorithm, we can derive a quite similar helpful lemma as we did for the follow the leader algorithm, in the sense that for any environmental data sequence we can think of, doesn't matter, for which the follow the regularized leader algorithm is choosing accordingly these actions A1, A2, or with the superscript FTRL. And we can bound the regret of the regularized leader with time horizon for time horizon capital T with respect to some competing action A tilde, which can be an arbitrary one in the action space. So it doesn't matter. So for sake of completeness, this is the definition of this regret with respect to some competing action A tilde. And we can bound it by this term here. And if you look closely, this resembles what we have seen for the follow the leader algorithm. Namely, this part is essentially the same as before, since we have here the cumulative differences of the follow the regularized leader algorithm as it is. So it's choosing in time step T the action which has the smallest cumulative loss for the data seen so far, plus regularization term, and does not use the information about ZT. And we compare it here with the loss of the cheetah version, so where we have this t+1, which would also include the knowledge of the ZT, yeah, which we don't know, of course, yeah, but again, this is a theoretical consideration which is used for proving the bounds on the regret. And because this is not enough to bound the regret with respect to some competing action A tilde, we have to add here these regularization terms, to be more precise, the regularization of the competing action and the very first action taken by the follow the regularized leader algorithm. The others are more or less cancelling out more, which can be seen quite similarly to the proof of the follow the leader algorithm, which we have done quite in detail with an induction. So here this can be shown quite similarly via induction as we did for the follow the leader algorithm. But again, rather the interpretation is more interesting, so we can bound here the regret of the follow the regularized leader algorithm with respect to some competing action A tilde by this term composed of the difference of regularization terms and the difference of cumulative loss of the follow the regularized leader algorithm and its one step look ahead cheetah version. And now we ask for what is one suitable regularization for the online linear optimization problem. So again, recall, an online linear optimization problem is characterized by the linear loss function, which is nothing else than the inner product of the action and the environmental data point. So in the one-dimensional case, it's just multiplication of them. And it turns out that a suitable regularization for this case is simply the squared L2 norm regularization, which is more or less avoiding the undesired effect that the action will be jumping from one extreme to the other. So it's always more or less kind of regularized to the zero. You see that here you make it, you make this term small if you choose an action which has rather small Euclidean length, and this is of course achieved by the zero, but the zero will not always be the one which is minimizing the cumulative loss for the environmental data points seen so far. So it's a kind of trade-off between the two. And for purposes of tuning more or less the algorithm, we also introduce here some regularization magnitude eta, which we divide here in the regularization function, the squared Euclidean norm. And we will see that we can tune this parameter, which we call the regularization magnitude at the first place. We can tune it such that we can have suitable, satisfactory, theoretical upper bounds on the regret for the follow the regularized leader algorithm in the online linear optimization problem. And first of all, let's see what happens with the choice, with the concrete choice of the action of the follow the regularized leader algorithm if we have this kind of regularization. Well, so in the worst case, remember, we have to solve a minimization problem to choose the action if the loss function is not so nice. But obviously, here we have a quite nice loss function, the linear loss, which we can minimize quite easily, or the cumulative loss over it quite easily. And even if we add here a regularization term, we can still minimize it quite easily and also get a closed form expression for the minimizer, which is given here. How can we see this? Well, let's recall to follow the regularized leader algorithm is the minimizer. Yeah, so again, abusing a bit the notation, writing here the equal sign, is the minimizer of regularization term plus loss, the cumulative loss, and we can already plug in that we are dealing with the linear loss, which is given here. So rewriting it a bit, also taking into account that we have here the squared L2 norm as a regularization. So we get here A transposed A 2 times eta, and in the sum we can use the fact that here this A is not depending on the summation index. You can write it in front of that. So it's a transposed, don't be confused here. And well, we can define this as a function f of a, which we want to minimize. Yeah, we want to find the minimizer of it. What's the minimizer of this function, which is, by the way, a linear function, a convex function, sorry, a convex function. So it's enough to look at where the gradient is 0 and solve with respect to the A. And well, what's the gradient? Here we have a quadratic term. Now this is a quadratic term. So we end up here with A eta, because the quadratic term will be 2 times the A, the variable for which we are doing the minimization or the derivation. And well, here we have a linear term, the second one, so the linear term remains. And well, now you see it, solving it with respect to A, this equation, you get exactly this representation. Yeah, so it's simply summing up the data points we have seen so far and multiplying it with minus the regularization magnitude. Yeah? So this is the closed formula for the follow the regularized leader algorithm for linear loss if we take the squared L2 norm as the regularization function. So what's the update formula for this action? Again, we have a quite nice update formula, namely the next action is given by the action before minus eta times the most recent environmental data point. And this is quite similar to a gradient descent. Yeah? So you have here the next iteration is the previous iteration with gradient, yeah, zt, if you think of it as a gradient with step size minus eta, is the direction, is the step size in which you take the update with the direction zt. And this can be interpreted to also in a gradient-like manner, which we will in fact do later on to deal with more complex online problems than online linear optimization. Yeah, so it's also fair to say that this eta has an interpretation of a step size if we have the linear loss and the squared L2 norm regularization due to this update formula, which is again a cheap update formula. We only have to keep track of the previous action and the previous environmental data point, but not the entire history. And we can derive the following theoretical guarantee for the regularized counterpart of the follow the leader algorithm. If we use squared L2 norm for regularization, if we deal with an online linear optimization problem where the action space is some subset of RD, we can derive that the regret with respect to some competing action A tilde, which can be any action you like, is bounded by this term, yeah? Where we have here one term depending on the competing action A tilde, or rather its squared Euclidean length, and a term which is depending more or less on the variation of the environmental data points in terms of their squared Euclidean lengths. And this is what you see. And to make life easier, we will show this result only for the case where the action space is in fact the RD, because if we consider the case that A is a strict subset, then it might happen that our action selection, the closed formula we have, might leave the action space A. So what would be the easiest fix? We would project it back onto A, which is meaning that we have to solve a minimization problem in the worst case again, yeah? So there's a price to pay, but still the analysis is quite similar. Only at one step we will see later, or on the next slide, we would have we would need to use the Cauchy-Schwarz inequality, yeah? But essentially the proof is still the same. Okay, so let's see how we can show this. Again, we keep track of our short-term reminder, short-term memory reminder box, where we have these two reminders here. One is the useful lemma we have talked about, which is quite similar to the one we had for the follow the leader algorithm. And the other is this update formula for the follow the regularized leader algorithm, where we have this gradient descent-like update, with the interpretation of eta as the step size and the environmental data point like a gradient in this case. Again, we make life easier, abbreviate or forget about the superscripts. Know that here we are always looking at actions from which are given by the follow the regularized leader algorithm. And well, what we want to show is a bound on this regret with respect to some competing action A tilde. We can use the first reminder, our helpful lemma, that this regret with respect to some competing action A tilde is bounded by the difference of the regularization terms of the competing action and the very first action, and well, the cumulative difference between the actions taken by the follow the regularized leader algorithm and its one step look ahead cheater version. And now we only have to plug in a couple of definitions. So again, recall what the regularization function was. It was A transposed A to eta. Yeah? So the squared Euclidean norm of the input divided by 2 times eta. This is what we can plug in here. We can forget about this here, because this here is always greater equals 0, so it's non-negative. So if we forget about it, we only make the entire right-hand side larger. Then we remember that we are dealing with an online linear optimization problem, so that the loss function here and here are nothing else than the inner products of the input pairs which we have here. Alright, then what we see now when we look at the current right-hand side, here and here we have the same terms, so we can conveniently write it like this by using the law of distributivity. And if we do this, we can quite conveniently use our update formula, which is stating, well, the difference between the updates is nothing else than minus eta, the current environmental data point. So this thing here is the same as minus eta, the current environmental data point. So what we would have here is, so not forgetting about the transposing of the two, so that this here is also transposed, what we would have here would be minus eta z transposed zt, and this here is nothing else than the squared Euclidean norm of zt. Also, here we have the difference the other way around, so the minus is in fact the plus. So we have here at minus at, so this here would be only this, because it's the other way around. So that we have here the plus. And this is what we wanted to show. This is the claim we had, the regret of the follow the regularized leader algorithm with respect to some competing action A tilde for a time horizon capital T is bounded by these two terms. Okay, so what is the purpose of this result? How can we use it to show something? Because right now we don't see any sublinear behavior or something like that. But what we see is we have here two terms, and both terms are having the opposite behavior with respect to the regularization magnitude or the step size, which we also call it. And this first term, the one where we have the eta in the denominator, this can be interpreted as a biased term. So we have that this regret upper bound is always biased by the squared Euclidean distance of the competing action. So it has always the impact that it's biasing towards this Euclidean length or squared length. So what can we do about this? So to reduce the influence of this bias term, we could use a higher regularization magnitude. So if we make the eta large, then this entire term will be small. So this entire, or the influence of the bias term will become small. However, there's also a second term, right, which can be interpreted as a variance term, because it's kind of tracking how much the environmental data points are varying with respect to their squared Euclidean length. And if we would use a high eta here, a high regularization magnitude here, then this term will be large, the overall term. So we would have here rather the tendency to make this here small, which is, however, in conflict with this. So what we need to do is we need to find a good trade-off for choosing the regularization magnitude such that both terms are kept in balance, more or less. Now we want to make the bias small by choosing a high regularization magnitude, but then the problem is that the variation term will be large. So we have a tendency to make it small for making the variance small, but then the bias will be larger. But of course, if we choose the eta in the right way, and we will see in a minute how we can do this, we can have here a satisfactory bound for the regret with respect to some competing action A tilde, which we only have to tune more or less. So with respect to the eta, we have to tune here, and then we get hopefully a nice result. And this will prevent the the unstable behavior of the follow the leader algorithm, yeah, because we are still dealing here with an online linear optimization problem for which we have shown this result. And the right choice of the regularization, meaning the right choice of the eta, will then guarantee that we have good regret upper bounds. All right, so graphically we have the following problem. The bias is going down with a larger regularization magnitude. The variance goes up somewhere where they are crossing, where both are somehow in a good balance. There, the overall regret bound will be optimal. And now the question is where can we find, or how can we find exactly this point, this optimal choice for the eta. And this depends again a bit on the concrete linear optimization problem we are dealing here in this online learning world. And we will assume that the competing actions, so more or less the action space, is such that every action, in particular all competing actions, are such that their Euclidean length is at most b, for some constant b. So remember, we can also use our previous, or show our previous result for such a case, that the action space is in fact a strict subset of Rd. And a quite similar assumption we had for the online quadratic optimization problem for the follow the leader, namely that the environmental data points are such that their largest Euclidean length will be bounded by some constant v. And then we can derive an optimal choice for the regularization magnitude. Namely, we can set it like this, so it's depending on these constants b and v, coming from here. And if we divide here by square root of 2 times the time horizon, then we can show that the regret, now see that here no competing action a tilde is involved anymore. So it's the regret where we compare with the best action in hindsight. This regret now is bounded by some constant term times square root of the time horizon. And this is a good result because it's again showing that the regret will be sublinear. So you have here something which is growing like the square root of the time horizon, and this is definitely slower than a linear growth. But there's, of course, one problem, that this optimal choice is depending on the time horizon. So we have here dependency on the time horizon. This is due to the simple way we derive this optimal choice. So also in the gradient descent, if you have knowledge about the smoothness or convexity of the objective function, you can show similar things, but usually you don't know it. And there are also ways to cope with that by getting rid of constants, by terms which you don't know. And in this online learning world, there's a similar thing for this parameter, or this meta parameter of the online learning problem, namely the time horizon, which is perhaps not known in advance. So perhaps you don't know how long the game between the learner and the environment will go on. Or even worse, it can also be infinite, so that you have here essentially a regularization of 0, which also doesn't make sense. But there's a trick, the so-called doubling trick, which is more or less quite easy to apply and does not need to know the time horizon, and you get still a similar result like this. So that the order, the dependency here of square root time horizon is still the same in the regret bound. And well, how can we show this? it's quite straightforward by using what we already have shown, namely that the regret with respect to some competing action A tilde is bias term plus variance term. Now we can make use of our assumptions. Our assumptions are stating that this here is always smaller than b squared, because the length, the maximal length, Euclidean length we can have for a competing action is b, so squaring it is giving us the b squared. The other assumption is that here these squared Euclidean lengths of the environmental data points, they are all smaller than this v constant, or squared rather, because we have here the squaring. So if we use it here, it's obvious that we obtain this bound. If we apply our assumptions for the variance term, what we are doing then is we are summing up t times the constant v squared, so that we get indeed this bound here. And now we can see that this bound is again independent of the competing action A tilde. Here we have a dependency on A tilde, this here is not depending on A tilde. So we can write here the supremum over all A tildes, which is corresponding to the regret, where we compete with the best action in hindsight. And still, using this supremum will be bounded by this right-hand side, which is unaffected by the supremum, which we get here. Okay, and now we have here as an upper bound essentially a function of eta, which we can minimize. So we can express it as a function f of eta, where for the first term the eta is in the denominator, in the second term it's in the numerator, and well, we can minimize this function with respect to eta. And if we do this, we will see, by plugging in then the constants a being b squared and b being t times v squared, that the minimizer will be attained exactly at the claimed optimal choice. And the resulting value of this function will be, as we saw before, exactly b times v times square root of the time horizon. And this is a quite typical way how to derive a theoretical guarantee, so that you first start with the regret with respect to some competing action A tilde. You derive something like this, like a bias variance term. Then you have a couple of assumptions on how to make the bias term and the variance term somehow independent of the competing action A tilde. You end up with a bound which needs to be tuned with respect to the parameter of the online learning algorithm, and you tune it. You tune it and then you know what the optimal parameter will be. So to conclude, what have we shown so far? The follow the regularized leader algorithm is a quite nice algorithm because it can deal with the online quadratic optimization problem simply by using no regularization at all, because it's then boiling down to the follow the leader algorithm, and for the follow the leader algorithm we already have seen quite nice theoretical results, and also that it admits a cheap update formula. That's just the empirical average over the data points. But if we are facing an online linear optimization problem, we can still use the follow the regularized leader algorithm if we use a suitable regularization function, which was in our case the squared L2 norm, where we have to tune the magnitude, the regularization magnitude, in a suitable way and still get then a satisfactory regret upper bound, and we have a quick update formula. So you have this gradient descent step like update. But of course, not all problems we are facing are online quadratic optimization problems or online linear optimization problems. Yeah? We have also other loss functions which are not quadratic, not linear. And the question is, of course, how can we deal with such type of problems? Yeah? And what we want is to keep both desired properties, namely that we have a reasonable regret upper bound for the online learning algorithm, and we want to keep track of the computational resources we have, in the sense that we don't want to use too much and accordingly want to have a quick update formula for the action choice. And how to get to this, how to tackle this question will be the topic for the next lecture.